This lecture is going to be involving measuring earthquakes. We're going to look at the Richter scale, the modified Mercalli intensity index, and the moment magnitude scales. And you're going to notice that we're going to start recognizing the amount of energy that's released in different sizes or different magnitudes of earthquakes. Let's first look at the IRIS seismic monitor map, and be sure to click on this link. This will show you today's or recent map of the Earth that actually shows earthquakes that have taken place. And I want you to take a look at the size of the scales and the different colors. They communicate to you. The red implies that they happen today. So red, so there's a very active planet, right? You're going to find this out. And you're going to see that in orange was yesterday, in yellow is the past 2 weeks, and pink is the past 15 years. Look at the size of the circle. The smaller the circle, the smaller the magnitude. The larger the circle, the larger the magnitude. So we can actually compare the IRIS seismic monitor map to an actual plate tectonic map. And notice where we find so much of the geologic activity taking place, we are actually able to see where the lithospheric plates that involve the Earth's crust and upper mantle, where these boundaries are interacting, and typically, but not always, where we find earthquakes. It doesn't always have to happen, or earthquakes don't always have to happen along the plate boundary. You can get what are called intraplate earthquakes and intraplate volcanism. Remember, we studied the Hawaiian Islands. So you have a hot spot there, you have Yellowstone National Park, you have a hot spot there. Those can also be associated with earthquakes as well. But if we compare the seismic monitor map to a plate tectonic map, you're going to see how they align very nicely. That if we look at the west coast of South America, so there's the west coast, here's the west coast of South America. Notice it's just very geologically active. We have a Nazca plate that's subducting beneath South American plate, and therefore we have a lot of tectonic activity. A lot of earthquakes are generated here. And notice we can follow this around to the Aleutian Islands of Alaska. Notice the Aleutian Islands of Alaska up here, very active. So we live on a very, very seismically active planet. And therefore the IRIS seismic monitor map shows us that. And it shows us in real time what is happening on Earth. We're going to explore the difference between a magnitude, like how intense, how much energy is in the earthquake, versus the intensity, kind of how people feel it and what it does to structures. So magnitude versus intensity of earthquakes. We'll start off looking at the Richter scale. It's a logarithmic scale that determines the energy of the earthquake. It doesn't actually measure large earthquakes very well, though. Then we have the modified Mercalli index. It determines the intensity of destruction from a destruction point of view, along with how people felt the surface waves. Notice that this is subjective. Building design, distances from the epicenter, and what the structure is built upon, whether it's built on solid rock, soil, gravel, those can all influence how much damage is done. So remember, this is an intensity scale. So Richter scale and moment magnitude measure magnitudes, how much energy. So the moment magnitude is a scale that determines several features of the earthquake. It's a more updated, a modern way to view earthquakes. And these are used for large earthquakes. So let's observe this graphic. The distance from the epicenter is measured on the far left column. These are generally in kilometers or in miles. The central line, or vertical line that we're going to be measuring is going to look at magnitude, which is generally measured on the Richter scale. And then the far right line, here it's in red, is going to measure the amplitude of the arriving waves. And then this far right-hand side is going to describe the energy released from the earthquake itself. Observe, we're connecting the magnitude to the amount of energy. So therefore, a magnitude of 4 is going to release 15,000. This is an energy equivalent to kilograms of TNT, 15,000 kilograms of TNT. So a 4 and a 5 have different amounts of energy. Notice, it's not like we're doubling. We're increasing with a logarithmic scale. And thus a magnitude 4 is only releasing 15,000 kilograms of TNT, whereas a magnitude 5 is going to release 476,000 kilograms of TNT. So it goes up very, very quickly. Increases are not what you think they are. They're going to go up exponentially or logarithmically. So in your binder, you're going to find a pictorial like this. We're going to be calculating the magnitude of earthquakes. So the magnitude of an earthquake references how much energy was released during the earthquake. This can be found using two pieces of information. The distance from the epicenter, here, your far left vertical column, and the amplitude of the arriving waves of the seismogram, here. The further one is from the epicenter, the less shaking, the less energy there is in the seismic waves that are arriving. This is measured in the form of the amplitude of the incoming waves. Generally, the Richter scale is used as a term for identifying the energy of an earthquake, but you'll find that it's actually been updated by using the moment magnitude scale. So look here, the closer, the larger amplitude of the incoming waves. So therefore, the amplitudes of the degree or the amount of shaking that a seismometer experiences. These are measured relative to a flat line, right? A flat line would say there's no earthquake, there's no energy of oscillation or shaking. So as soon as it starts shaking, that seismometer is actually oscillating back and forth, and it's picking up the readings measured in amplitudes. So let's label this. Let's make sure we realize this is our distance from the epicenter. This is measured in kilometers in your binder. 1 kilometer, or 1.6 kilometers, is 1 mile. So we can actually convert these. Notice your middle is a magnitude scale. It's a Richter scale. We can convert this into amount of energy that is released in the earthquake. And lastly, your final right column, that's an amplitude in millimeters. Notice that in 1 centimeter, there are 10 millimeters. So notice, if this is 20 millimeters, that would be 2 centimeters. So let's connect this to what we've done in the past. You'll see a characteristic pattern. The P waves arrive first, and they travel because they travel the fastest, yet they have the smallest amplitudes. S waves arrive second, because they travel slower than P waves, but they travel faster than surface waves. Observe this larger amplitude, the larger amplitude of the S wave than the P wave, yet smaller than surface waves. And finally, surface waves arrive last. They travel the slowest, yet they do the damage to structures. These have the largest amplitudes. So let's compare this to an example seismogram. We should follow that very pattern. Primary wave arrives first, has the smallest amplitude. Secondary waves, or your transverse waves, arrive second. Larger amplitude than P waves, but smaller than your surface waves. And then your surface waves roll in. And these are what are the high amplitude. These are what do damage. We see this because they travel at different speeds. So we no longer have to be at a location in order to sense it. We use remote sensing technology. Essentially, there are satellites. When you follow a wave on the Earth's surface, it can be done remotely. Technology allows scientists to follow the waves traveling on the Earth's surface. P waves, S waves, Rayleigh waves, and Love waves, or your surface waves, along the surface as they move within rock and get recorded at seismic stations. You can see this with the tsunami. I'll play this picture and I'll read it to you, or play the video. When a tsunami is generated, ocean waves can be followed on the ocean surface, coupled by early warning detection, which are just simply buoys in the water, and seismic equipment that are used for identifying where the earthquake took place. Here we see the tsunami that was generated several years ago, right around Christmas. And you can actually see the wave fronts traveling outward from the location of the actual epicenter. And so when you look at this, you can actually follow this wave front that's just moving outward. And it did tremendous damage. I believe there were around 300,000 people that were reported as killed from this. Notice, the entire oceans were affected by this. And the tsunami took a long time to race across the ocean. But it was traveling. It was actually traveling faster than a jet airliner. So let's look at the Richter scale. The Richter scale is a scale that is used to find out how powerful an earthquake was that is determined by seismographic readings. The Richter scale was named for the American seismologist Charles Richter. He lived from 1900 to 1985. It's one of the several very closely related methods that seismologists use to quantify the strength or magnitude of an earthquake. The Richter scale goes from 1 to 10. 1 meaning you could barely feel the earthquake. It's not likely to do much damage at all. It can be detected only by a seismograph. But a 10 meaning that it was the most powerful earthquake that you could have. It would be an upper limit. An earthquake with a magnitude 10 would lead to total devastation. If you look at this, as you're increasing the amount of energy released, right, measures the energy in the waves emitted from the earthquake, as you continue increasing in magnitude, you can actually get a kind of a comparison as to what that would lead to. That a 2 to a 2.9 would be hanging object would be swinging, 3 to 3.9 comparable to the vibrations of a passing truck or large truck. 4 to 4.9 may break windows, cause smaller unstable objects to fall. A 5 to 5.9 furniture moves, chunks of plaster may fall from walls. A 6 to 6.9 damage to well-built structures, doing lots of damage to poorly built ones. 7 to 7.9 buildings would be displaced from their foundation, cracks in the earth, underground pipes would be broken. 8 to 8.9 bridges would be destroyed, few structures would be left standing. And last, 9 and over, near total destruction. The waves moving through the earth would be visible to the naked eye. You could actually see them ripple. But I want to make sure we're clear with this. Because it's logarithmic, technically there's no upper limit to the Richter scale. Be sure to click on this video and watch it. It's really good animation. It compares the Richter scale to the moment magnitude. Because seismic waves weaken as the distance between the earthquake focus and the seismograph increases, like that of light, further you are from light or sound, it actually appears either dimmer or quieter. Richter developed a method that accounted for the decrease in wave amplitude with increased distance. The Richter scale is logarithmically based, which means that a 10-fold increase in wave amplitude, or the energy, corresponds to an increase of 1 on the magnitude scale, but this equates to a 32-fold increase in energy. So let's compare a 6.5 magnitude to a 5.5. The 6.5 magnitude earthquake would have 10 times a greater amplitude to that of a 5.5, yet 32 times more energy than a lower magnitude 5.5. And you can see here on the Richter scale is that you wouldn't even feel up to about a 2 or a 3. You wouldn't even notice it. However, when you start getting into 5s and 6s, you start having some moderate damage. And finally, when we get into 6s and into 7s and above, you start talking about tremendous amounts of damage. And here are some examples of earthquakes that have taken place over the past that are measured along the Richter logarithmic scale. So now let's look at the modified Mercalli index. This is an intensity that was developed using California buildings as its standard, or its proxy. It's appropriate for use throughout most of the world to establish the strength of an earthquake and the damage done by the earthquake. But the intensity of scales are based on the effects, the destruction of earthquakes, that depend on the severity of ground shaking, but also as much as population density, building design, and the nature of the surface, like what the structure was built upon. So understand that there are different regions that have a high population density, or that have a low population density, that even though it might be really powerful, it might not do much damage. And there are some that are in highly dense areas of populations that are just poorly designed, or they're built on something that would be readily moved. So there's somewhat of a subjectivity to this. But if you look at the modified Mercalli, you can simply just see here that the damage, when you get up to the 12 scale, it's almost total damage. Whereas an 11 scale would be, even rails on trains would be severely damaged, and pipelines would be severely damaged. So you have a scale here that is subject to a couple variables that makes it a little bit more subjective, less quantifiable. And finally, we get to the moment magnitude scale. Be sure to watch this video. It's a good video, good link to it. The moment magnitude scale is a more precise measurement of how much energy was released at this earthquake focus. It's based on 3 values, or 3 conditions. The average amount of displacement along the fault. In other words, a lot of times when you get slippage of, say, a subduction zone, or slipping of the oceanic crust that's subducting itself, it doesn't just move in one point. It could be over a large area. So therefore, the area of the rupture of the surface is important too. So the area in which there was movement, and then the amount of displacement. And then number 3 is the shear strength of the faulted rock, a measure of how much energy a rock can store before it slips and releases the energy in the form of an earthquake. So the moment magnitude earthquakes values are better for describing large earthquakes. So sometimes you'll hear a Richter scale measurement, sometimes you'll hear a moment magnitude scale, and they're not the same. That a Richter scale quantity can be lower or higher than a moment magnitude. That the moment magnitude takes into these 3 variables into consideration. So when we consider the moment magnitude, we'll just call this a much more updated, much more modern view of energy released within earthquakes. And so this is an energy that's measured, once again, in kilograms of explosive, generally TNT. And we've had all kinds of different earthquakes. And we have small earthquakes all the time. Not a lot of energy released in them. But as soon as we start getting into larger amounts, you just have tremendous amounts of energy that's released from the stored energy of the rock that's about to move. And so you can actually get comparisons. Here are actual times and locations which you had earthquakes. These are kind of giving you some perspective on them. That a low energy earthquake would be like a moderate lightning bolt versus an Oklahoma City bombing, and versus a large lightning bolt. And we compare it to an average tornado, and then a Hiroshima atomic bomb, and then Mount St. Helens eruption. Here we're comparing it to a large nuclear test. And then Krakatoa. This was one of the loudest sounds ever on Earth. So this side over here gives you some perspective as to what the moment magnitude is telling you over here on this side. But it all comes back to the amount of energy released.